Hello, in today's lecture, I'll be introducing ultrasound elastography. So let's begin with first understanding what is elastography and why is it needed. So we know that pathology alters tissue mechanics. So if a person has any injuries, inflammation, fibrosis, which is a buildup of extracellular matrix proteins in the tissue, and tumors, which can lead to cancer. Typically, when these diseases are diagnosed, you would present yourself or the patient would present themselves into the clinic, and the first thing the clinician would do is to palpate different regions of your body to assess whether there are any changes in the mechanical properties of your tissue. So this type of procedure is called manual palpation. So you can see in this image here on the left, you can see that a boy who's a patient is lying down and a nurse is palpating the abdominal area, probably looking for any variations in the location and the stiffness of the organs within that area. Here also, this is typically a procedure in which if you present yourself with some sort of cold, right? Typically, that type of inflammation can cause your lymph nodes, which are these glands below your neck right here, below your jaw. They get inflamed when there's a certain inflammation or a infection in your body. So what the doctor or nurse typically do is they feel these areas right here to see if there are any enlargement or any stiffness changes in those glands. So it's been well known for hundreds of years that the biomechanics of tissue can change whenever there is an injury or a disease. And the clinicians would use this manual palpation method to be able to gauge the severity of this disease. In terms of quantifying the mechanical properties of tissues, because we know manual palpation typically looks into the stiffness from a superficial point of view. But if you want to look into exactly and quantify what the stiffness of the tissue is, then typically what is done is you would apply some sort of load onto the tissue. You can measure the deformation or the response to the load, and then relate the response to a certain mechanical property. What is typically done in labs is that you would get a sample of a tissue that's either excised from a cadaver or even tissue constructs that are made. You would put them onto a mechanical testing device, such as this that you can see here. And what this mechanical testing device allows you to do is to apply a deformation onto the tissue, and then it allows you the person to measure exactly how the tissue responds to that deformation. There are several mechanical properties that are of interest, such as stiffness. Stiffness is the tissue's resistance to deformation. We know the stiffer the tissue, then the higher it is likely to resist that deformation. Elasticity. Elasticity is the ability of the tissue to return to its original shape. So for example, if you have a rubber band which is fairly elastic, if you stretch it and you stretch and deform, you release it, and then it will come back to its original configuration. Viscosity is another parameter, and that's a measure of the internal friction within the tissue that resists the deformation. Typically, the viscosity term is more applicable to liquids. However, your body is made up of mostly water, and therefore your body is estimated as a viscoelastic type of medium. Let's just give you an overview of the different mechanical testing techniques that are being used currently. So here's just an example of a tensile testing type experiment, where let's say you have your uniform material here that is represented by this cylinder. It's a very simplistic example of the tissue, but one can do this type of experiment. You affix that material onto a wall, which is denoted by this here, and then you apply some sort of force, a tensile force that will stretch that tissue. So then the original length of this tissue is denoted by L0, and when you apply that force, then the tissue deforms. And in this case, the tissue will lengthen by a increment of delta L here. So the stress that is measured or that is applied onto the material is denoted by this sigma parameter here, typically in newtons per meter squared or in pascals, and that equals to the force that is applied onto the material divided by the cross-sectional area. So for this cylindrical material here, the cross-sectional area would just be a circle right here. So stress equals force divided by the cross-sectional area. And in terms of the measure of deformation or the displacement of that material, we usually utilize strain as our parameter here, where it's denoted by this parameter epsilon, and that equals delta L, which is the change in length or the deformation, divided by the initial length, L naught, right here. So if you apply a certain stress to the material, a certain force per unit area, you keep increasing that stress. The strain will also increase linearly if you have a perfect elastic material. So you might have remembered from your previous physics class, Hooke's law. So here for a perfect elastic material, Hooke's law is the Young's modulus equals the stress divided by the strain. And we know from this stress-strain curve, assuming that you are within the linear elastic regime, then the slope of this stress-strain curve is the elastic or the Young's modulus, denoted by E here. Now, of course, if you keep stretching the material behavior will change. There'll be some other deformation or plastic deformation that will occur. And what that means is that if you stretch the material, it will not go back to its original position. There's also another situation where you keep increasing the stress of that you're applying into the material, and that will cause the material to break. So that is related to yield point. But in this case, in terms of material behavior, we're quantifying it using the elastic modulus. So then here we assume that we're still in the linear elastic regime. So again, the Young's modulus is a measure of the stiffness of the material. It's the ability of the material to withstand any changes in length when under tension or even compression. So in the previous example, we talked about tensile tests, but you can also get the elastic material or the Young's modulus using compression tests. So typically an elastic material is modeled as a spring, like a spring. If you stretch it, you release, it will go back to its original position. So here's just an example of, let's say, a material that is modeled as one layer having a soft spring, a middle layer having hard spring, and then the bottom layer as being represented by a soft spring. This is how it looks before compression. Now, if you apply some sort of compressive force onto that material, you would get strains associated with each of these regions. And we know that for a softer spring, the strain would be much higher than a stiffer or a harder spring, as you can see here. Another parameter of interest is the bulk modulus. So the bulk modulus is the ability of a measure of the material to withstand changes in volume when under compression from all sides. So if you can imagine, this is a material here, an object that is in which a compressive force is applied on all sides. So this is similar to when you drop an object into the ocean. As you go deeper into the ocean, the pressure at deeper regions of the ocean will get much, much more. And eventually, as the object is going down deeper depths into the ocean, it will feel a lot of compressive force due to that higher pressure deep in the ocean. So basically, it also depends on the bulk modulus of that object to be able to withstand those pressures. So here, as you are applying that force, you will also be measuring some sort of strain. This is called bulk strain. And what the bulk strain is compasses of the change in volume divided by the initial volume of that object. So the bulk modulus is also an important parameter. It's the bulk stress divided by the bulk strain. And you can equalize that to the negative pressure times the initial volume divided by the change in volume. Another important parameter when we're talking about properties of tissues is the shear modulus. Here, let's imagine an object that is affixed to the bottom and a force is being applied on the lateral direction right here on the top surface of that object. So you're applying a shear stress and it's denoted by the term tau. That equals to the shear force divided by the cross-sectional of this top section of the object. And as you are applying that force, the object will shear and it will go into this configuration. The top portion will displace by a distance delta x here. And the shear strain, which is denoted by gamma, is calculated as the delta x divided by L, which is the height of this object. So you can measure a shear modulus as well. Shear modulus is typically denoted as G. That equals the shear stress tau divided by the shear strain gamma. And it's the measure of the material's resistance to shear deformation when subjected to a stress. Another important parameter that let's consider is the Poisson's ratio. And what this is, it's basically the ratio of the transverse strain divided by the axial strain. So if you could imagine, if this was the initial tissue right here, object, dimensions right here, if you apply a certain force that will cause a tensile deformation, the y part or the lateral width of the object will also decrease as you are stretching the material in this axial direction. So the transverse strain is denoted by here and the axial strain is denoted as here. And typically soft tissues have a higher water content. So the Poisson's ratio is typically around 0.4999, which is what is assumed. It's considered a nearly incompressible material. So what it means to be incompressible is that the volume does not change under any applied deformation. Now, similar to water, water is incompressible. If you compress water, it will also deform in another direction, but the volume of the water will not change. So tissues are typically assumed as nearly incompressible. Now let's put together the concepts of the modulus and the wave sound speeds that we encounter in ultrasound. So we've already talked about longitudinal wave propagation. As a review, this is when the particles in the tissue or the material oscillate parallel to the direction of the wave propagation right here. Now, this is typically used in imaging by the pulse echo method, and the frequencies associated with this is around megahertz frequencies. So the bulk modulus actually, which we denote by K, equals the density of the medium times the square of the longitudinal sound speed. So for soft tissues, the longitudinal sound speeds range around 1480 to 1540 meters per second. And the bulk modulus range on the order of gigapascals, so 10 to the 9th pascals, typically around 2 gigapascals, but within this one order of magnitude. When we talk about shear wave propagation, this type of wave is mainly used for elastography. So shear waves, what happens in there is that the particles oscillate perpendicular to the direction of the wave propagation. And typically the frequencies of shear waves are less than 1 kilohertz. The shear modulus now, which is our material parameter G, equals the density times the shear wave speed to the squared. So for soft tissues, the shear wave speed ranges on the order of 1 to 10 meters per second, while the shear modulus ranges on the order of 10 to the 3rd to 10 to the 8th pascals, or 1 to 100 kilopascals. So this is over almost 5 orders of magnitude. And the reason why elastography, the field itself, utilizes shear wave instead of longitudinal waves to get the modulus properties, it's because of this wide range of shear moduli. That will allow you to differentiate different types of tissues, especially which is important for tissue diagnosis. Now, in elastography, the Young's and shear moduli of soft tissues are typically interchanged, and that's because of certain assumptions. So if you assume that the media is isotropic, meaning that the material response is the same in both directions, in all of the directions. If you assume that the material is homogeneous and nearly incompressible, so that's why we talked about the Poisson's ratio. So incompressible material has a Poisson's ratio of about 0.5. Soft tissues are typically assumed to be 0.499, very close to 0.5. And if you assume that the material is elastic, right, then the Young's modulus can be related to the shear wave speed or the shear modulus by this equation here, where the Young's modulus is 3 times the shear modulus right here. Now, this is the general expression for the relationship between Young's modulus and the shear modulus. But if you plug in 0.5 in this equation, it becomes 3 times the shear modulus here. So if you, in elastography, we typically use the shear modulus. Now, if you would like to estimate what the Young's modulus is, then under these assumptions, now these are fairly simplistic assumptions of the material, then the relationship between the Young's and shear modulus is just by a factor of 3. So we'll talk more about this when we get into shear wave elastography. Now, elastography in general, another term for it is elasticity imaging. So imaging the elastic properties of tissues. Now it's more of like imaging the mechanical properties of tissues, because we don't only get the shear modulus, we can also get the plot the map as a function of the shear wave speed as well as viscosity. So just giving you an example of what an elastography or an elastogram looks like. So here we plot the B-mode image down here. And there are some carcinoma regions around this location. But you can see that sometimes in B-mode images, tissues appear isoechoic, or these tumors appear isoechoic or relative to the background surrounding tissues here. So it makes it challenging for the clinician to be able to determine exactly where the lesion is. And what elastography allows you to do is allows you to give more contrast to your image based on the mechanical property. So what you see here on the top is what's called an elastogram, an image of the elastic properties of tissue. We have a scale bar here that's in terms of the Young's modulus. And what you can see in this map is a color map where red appears more stiff and then blue corresponds to a region that's less stiff. And for these type of cancer, typically the tumor is more stiff than the surrounding tissue. So here you see that it's more red in this region. I've just shown you an example of one type of elastography technique, but there are several types, and I will show you a couple of these. So the first method we'll discuss is strain imaging. And what it does here is that you send a type of push or a compression onto the tissue and you measure the deformation of the tissue, similar to our compressive testing that I described earlier. Now, the way this table is arranged is based on its excitation method, the technique, the name of the technique that is being used, and what type of measurements it's being outputted. So for strain imaging, you can either excite by manually compressing the material. You can either use the natural motion of the body. So for instance, the cardiovascular, the vascular pulsations, the respiratory motion as a person is breathing. So this technique uses is strain elastography. And a couple of the measurements that are shown here are normalized strain. Some geometric measures can be assessed in strain elastography and strain ratio. And we'll look at even others that are used to be able to assess tissues. Now, the next one is shear wave imaging. Now, this utilizes the shear wave that is being generated into the tissue. You can create this shear wave using a transducer that will send an acoustic radiation force impulse. So we'll talk more about this in the next lecture. A couple of the techniques are point shear wave speed measurement and shear wave speed imaging. And that can give you the measurement outputs of shear wave speed. And if you apply our equation, assuming isotropic, homogeneous elastic medium, then you can also compute the Young's modulus. And the third set of techniques that we'll also discuss is the transient elastography technique. And in this case, the type of excitation method is external mechanical vibration systems. So this is an electromechanical instrument where it vibrates the tissue, and that causes propagation of shear waves inside the tissue. And this will allow you to measure the Young's modulus. So in the next lecture, we'll talk more about transient elastography. Now let's first start with strain elastography. So as I had mentioned, what happens is that you first take an image of the material, the tissue, and then compress, and then take another image right here. So you would take an image before and after compressing the tissue. You can also compress with your transducer itself. So you put the transducer on top of the material and compress it by hand. And based on that, you can create an image of the strain. So here, what I show is an image of a normal kidney. On the left is the B-mode image, and on the right is your strain image here. The color bar here is the measurements of strain. So soft material will have more strain because it's easier to displace, so it'll appear red in the image. And then a stiff material will have less strain, so it'll appear more blue. So this is of a normal kidney right here. You can see in the B-mode image delineation of that normal kidney. If there was any disease or injuries in the kidney, then one would be able to look at a strain image and see whether there are any differences in the stiffness or the strain of the tissue relative to a normal kidney. So going back to our elastic spring model here. So when you apply the compression, again, you're assuming that the tissue is elastic. So if you have a softer spring, it will displace more. And if you have a hard spring, it will displace less. And the spatial derivative of displacement is actually the strain. And so this is how you can relate the strain to the displacement of the tissue as you're applying the compression. Now, the tissue deformation is monitored spatially and temporally just using typical ultrasound pulse echo imaging. I will talk about 3 methods that are used to estimate tissue displacements. So the first method is the spatial correlation method. And what it is, it measures the differences between the reference signal, so which is before compression, and the signal ultrasound, a signal that you would get from the tissue after compression. And it uses the cross-correlation algorithm. You're computing a time shift, okay, in the signal. So for example, here on the left, we see the black. This is as a amplitude as a function of time. The black curve corresponds to the post compression, and the blue dotted is the pre-compression right here. And you can see that there is some sort of shift in the signal during time. When you apply a cross-correlation between these two signals, it will compute it and will produce a cross-correlation coefficient as a function of the time lag, something similar to this. And the peak of that correlation coefficient will get you the time lag. Here in this case, it's delta t. And then how you can compute the deformation or the displacement of the tissue is by using the range equation that we have discussed before. So the displacement here equals the longitudinal sound speed times this time lag divided by 2. Now this will be on the units of meters. Another method is the phase difference detection method right here. So it looks into the differences in phase of a portion of the signal before and after compression. So you can see here, this is what a signal would look like before compression. After compression, it might look something like this. If you zone into, if you window a certain portion of the signal, and look at the phase differences, then you can also compute the displacement based on this phase by using this equation. You have the displacement equals the phase divided by 2 pi times the frequency, all of that times the longitudinal sound speed. So these are 2 methods to compute. Now, there are trade-offs between each of these methods. So first, here I show the trade-offs with respect to real-time capability, as well as the amount of displacement that can be measured with the time shifts. So for example, for the spatial correlation method, it has really high computational complexity because you would have to calculate the correlation coefficient. Whereas the phase difference method, it has a good high-speed operation, so it's much faster than the spatial correlation method. The advantage of the spatial correlation method is that it can measure displacement exceeding the wavelength of the ultrasound. So another name for the spatial correlation method is actually speckle tracking method. This is widely used. But the phase difference method, although it has better computational efficiency, it can only measure displacements up to half of an excitation wavelength. So what has been done now is to combine the benefits of both spatial correlation and the phase difference algorithms. So now I'll talk about this combined autocorrelation method that has been implemented into clinical scanners. So for example, here you have your signal before you compress the tissue and the signal after you compress the tissue right here. There will be a time shift that will be computed. So to be able to do this combined autocorrelation method, first you do a coarse estimation of the displacement. So this is similar to the speckle tracking algorithm, where in this case, you first compute the envelope of the signal here. So we're going to detect the envelope here, as you can see. And then we would detect the envelope also for the post-compression signal. And then what you would do is you would perform autocorrelation to be able to detect the large displacements. Subsequently, if you look at the carrier signals here, you would detect the phase difference from the carrier signals pre and post compression to be able to detect the smaller, less than half a wavelength, small displacements. So both these methods use the autocorrelation method. And what it has been found is that it improves the accuracy in strain estimation, and it has been able to measure strain within the range of 0.05 to 5% strain. And compared to the other two, it also has good computational efficiency. So this combined autocorrelation method is typically used in clinical scanners now. Now, there's been a lot of research and looking into other displacement tracking algorithms, but I would welcome you to look into those algorithms. However, they're beyond the scope of this course. Looking into the clinical applications of strain elastography now. So strain elastography has been widely used for detecting breast tumors. It's clinically used currently. Also, you can utilize the vascular pulsation or the pulsation of your blood vessels, or either the respiratory process to be able to evaluate the stiffness of plaques in your carotid arteries, or also monitor liver fibrosis. So this is what's being used now. So on another example here is ability to detect prostate tumor using strain elastography. So you can see here, this is a B-mode image of a prostate with a tumor. It's very challenging, difficult to see with an untrained eye exactly where the tumor is. But if you look at the strain image here, you can see that you can see a red region right here that has higher strain relative, and it's much different to the surrounding tissues. And this, if you compare it with histology, this is a part where the tumor is. And basically, one can correlate the strain and the histological sections to be able to exactly identify that this is a location where the tumor is. Another application is elastography of disease invasive ductal carcinoma in the breast right here. So this is a nice image that shows you motion that's being applied in the ultrasound image of a tissue here. And you can see the strain being calculated almost in real time. So these kinds of images can be able to help the clinician assess exactly where the tumor is. Now, strain elastography is fairly easy to use. It can provide strain images with almost pixel resolution, but there's several limitations to these techniques. So first, since one does manual compression, it is difficult to calculate the actual stress distribution that is inside the body, right? Therefore, it's typically considered as a qualitative technique. So it's also very challenging because of its nature. It will be challenging to perform any quantitative comparisons between different cases from different patient to patient. However, there are several efforts to be able to try to get some quantitative metrics from the strain elastography images. So I'm going to introduce some of the semi-quantitative metrics that are being used today. So some of these metrics include normalized strain, which is just a measure of the strain divided by the max strain. Typically, the strain will vary depending on the region. If the tumor is there or the diseased region is there, then the strain will change. Also, some geometric measures can be gained from the strain elastography image. You can look at the size or the shape of a low strain area. You can also calculate a strain ratio. And typically how that's calculated is you select a region outside of the tumor and a region inside of the tumor. So here, a mean strain here of B is the reference area outside of the tumor, and the mean strain of A is actually the tumor lesion area. So depending on these strain ratios, it will change, you can detect whether the lesion is there. And then here, this is a E to B ratio. So what this is the ratio of the diameter of the lesion in the strain image versus the diameter in the B mode image. So here's just an example where I show that in the B mode image, the clinician is trying to measure the size of the lesion. In the strain elastogram image here, you can see that there could be some differences in the size of the lesion as well. These measures are being used today. However, one should note that these strain measurements only look at the local differences in the strain within one strain image. So it's very challenging to be able to compare these types of metrics from one patient to the other. So to interpret these, it should be done under caution. I'll also introduce another elasticity score that is widely used in breast cancer diagnosis. So what this is the Tsukuba score, which looks into the pattern of the strain elastography images. And depending on that pattern, it will categorize the tissue as benign or malignant. So you can see this is a 5-point scale, and depending on the pattern here, the clinician can either score it as benign or malignant, and in the intermediate stages as well. I hope this gives you a good overview of the physical principles that are being utilized in elastography. We talked about the different modulus, bulk, Young's, and shear modulus, especially the Poisson's ratio as well, and how these are interrelated depending on the assumptions that we have. We also talked about the relationships between the sound wave speeds and the modulus of soft tissues. So for instance, if you can measure the shear wave speed, then one can also measure the shear modulus, depending on certain assumptions, of course. We also went through a list of ultrasound elastography methods. And in particular, we delved deeper into strain elastography, how it's being developed, and what are the clinical applications of this technique. So in a subsequent lecture, we'll talk more about the shear wave imaging techniques. That's all for today. I'll see you in the next lecture.